plunge past the sunlit shallows beyond the reach of the most powerful photosynthetic rays, and you enter a realm of absolute deprivation. At 3,000 meters below the surface, the deep ocean is a crushing void where pressure exceeds 400 times that of the atmosphere and temperatures hover just above freezing. Here, the complete absence of solar photons creates an eternal, suffocating midnight. It is an environment that seems entirely hostile to biology, a barren wasteland where survival should be impossible. Yet out of this profound darkness, a sudden electric blue spark shatters the abyss. Then comes another, followed by a cascading constellation of emerald and sapphire flashes. The deep sea is not a dead zone, but a bustling metropolis illuminated by the creatures that call it home. This living light is not merely a beautiful anomaly. It is a brutal, necessary currency for existence in a world where seeing and being seen dictates who lives and who dies. This phenomenon is known as bioluminescence, the emission of light by a living organism. Unlike the thermal radiation of a campfire or an incandescent bulb, this is a cold fire, generating illumination with nearly zero wasted heat. Scientists have discovered that this extraordinary ability has evolved independently across marine lineages dozens of times. It represents a masterclass in biochemical engineering, a testament to the sheer ingenuity of life when pushed to the absolute limits of endurance. The specific mechanisms behind this glow rely on highly orchestrated chemical reactions. At the core of this process is a light-emitting molecule called luciferin, which reacts with oxygen. This reaction is catalyzed by an enzyme known as luciferase, triggering a rapid release of energy in the form of photons. By strictly controlling the flow of oxygen or the concentration of these chemicals within specialized cells, deep-sea animals can dictate the exact intensity, duration, and color of their luminous displays. Not all inhabitants of the abyss manufacture their own chemical fire. Some rely on a remarkable evolutionary partnership, cultivating colonies of symbiotic bacteria that possess the innate ability to glow. These microbes are housed within highly modified glandular structures called photophores, which the host animal can cover or expose using muscular flaps like biological shutters. In exchange for a safe, nutrient-rich haven within the host, the bacteria provide the crucial illumination needed to navigate the treacherous depths. No creature exemplifies the sinister utility of this light, quite like the anglerfish. Drifting silently in the bathypelagic zone, this predator is a nightmare of jagged, translucent teeth and a distensible stomach. Protruding from its forehead is a modified dorsal fin spine, acting as a biological fishing rod. At the tip of this appendage sits the esca, a fleshy lure packed with those glowing symbiotic bacteria, pulsing with a faint, irresistible luminescence in the pitch-black water. In an ecosystem where meals are separated by vast distances and immense stretches of time, expending energy to hunt is a deadly gamble. The ambient glow of the lure solves this profound caloric deficit. Instead of chasing prey through the crushing pressure, the anglerfish simply waits. Curious crustaceans and smaller fish, drawn to the solitary beacon like moths to a flame, swim directly toward the jaws of the ambush predator, realizing their fatal mistake only as the trap snaps shut. The evolutionary brilliance of the anglerfish's lure extends beyond mere attraction. Research indicates that the specific strain of bacteria housed within the esca cannot survive freely in the open ocean. They are entirely dependent on the host for specific chemical precursors to fuel their bioluminescence. This obligate symbiosis reveals a profound interdependence, demonstrating how extreme environmental pressures forge unbreakable biological alliances that defy the isolated nature of the abyss. Farther down, in the suffocating stretches of the oxygen minimum zone, the challenges of survival multiply. Here, the water is nearly stripped of dissolved oxygen, creating a suffocating layer that most marine life cannot tolerate. Yet this is the domain of the vampire squid, an ancient cephalopod that is neither a true squid nor an octopus. Its dark red skin and webbing between its arms give it a formidable appearance, but its true defense lies in its mastery of light. when threatened in a realm where traditional defensive ink would be invisible and useless. The vampire squid deploys a startling alternative. Instead of a dark cloud, it ejects a thick, viscous cloud of bioluminescent mucus from the tips of its arms. This glowing, sticky substance erupts into a dazzling cloud of blue orbs hanging suspended in the freezing water. The sudden, overwhelming burst of light serves a singular, desperate purpose. The luminous cloud completely disorients the attacker, overwhelming its highly sensitive, dark, adapted eyes, while the predator thrashes against the glowing decoy. Temporarily blinded by the sensory overload, the vampire squid propels itself backward into the shadows. By the time the chemical fire of the mucus fades, the cephalopod has vanished entirely, leaving the confused hunter grasping at nothing but cold, glowing water. Moving upward from the abyssal floor to the mesopelagic zone, often called the twilight realm, the darkness is no longer absolute. Here, between 200 and 1,000 meters deep, a faint, ghostly downwelling of sunlight manages to penetrate the water column. While insufficient for photosynthesis, this residual light creates a deadly backdrop. Any creature swimming above a predator will cast a distinct, fatal silhouette against the dim blue glow of the surface. To survive this lethal game of shadows, countless mesopelagic species have developed an ingenious form of camouflage known as counter-illumination. Lanternfish, hatchetfish, and various squids possess dense clusters of photophores along their ventral or bottom surfaces by precisely tuning the intensity and wavelength of the light emitted from their bellies. These animals can perfectly match the ambient light filtering down from above. This active camouflage effectively erases their silhouette. To a predator lurking below and looking upward, the prey simply vanishes, blending seamlessly into the faint sunlight. The sophistication of this adaptation is staggering. Many species have specialized optical filters and reflective tissues within their photophores that perfectly mimic the specific angular distribution and color temperature of the ocean's twilight, rendering them practically invisible in an environment devoid of physical hiding places. Documenting these ethereal displays has pushed human engineering to its absolute limits. The deep ocean is fiercely guarded by physics. At the depths where bioluminescence reigns, the hydrostatic pressure is sufficient to implode standard submersibles, warp solid steel, and shatter reinforced glass. Early pioneers of deep-sea exploration descended in cramped, spherical steel bathyspheres, peering through tiny quartz windows to catch fleeting glimpses of alien sparks, unable to capture the magic on primitive film. Those historical expedition logs describe a dizzying array of lights, a biological fireworks display that defied all prior understanding of marine biology. Yet, proving these accounts required decades of technological innovation. It took the development of robust, remotely operated vehicles and titanium-hulled submersibles to safely plunge oceanographers back into the abyss. These modern explorers face freezing temperatures and the constant looming threat of catastrophic pressure failure just to witness the hidden lives of the deep. Even with advanced submersibles, capturing the cold light of bioluminescence on camera presents a monumental challenge. Standard underwater lighting instantly blinds the creatures and washes out their natural glow, while the bioluminescence itself is often too faint for conventional lenses. Scientists had to develop ultra-sensitive low-light cameras, often adapted from astronomical telescopes, to finally record the specific mechanisms of deep-sea illumination in situ, revealing a world far more complex than previously imagined. The footage gathered from these daring dives has unveiled that light is not merely a weapon or a shield, it is a sophisticated language. In a boundless ocean with no landmarks, finding a mate of the exact same species is a statistical improbability. Bioluminescence bridges this vast emptiness. Certain species of deep-sea shrimp and bristlemouths use precise, rhythmic flashes to signal their presence, transforming the dark water into a sprawling, interconnected communication network. These flashes function as an intricate Morse code of survival. The frequency, duration, and spectral output of the light are unique to each species, ensuring that a signaling male attracts a suitable female rather than a hungry predator. Some creatures even possess dimorphic light organs, where males and females glow in distinctly different patterns. This luminous language is the invisible thread that binds populations together, ensuring genetic continuity in the most isolating environment on Earth. When considering the sheer volume of the deep pelagic zone, a staggering realization emerges. Because the deep ocean constitutes over 90% of the habitable space on our planet, and because the vast majority of its inhabitants utilize light, bioluminescence is likely the most common form of communication on Earth. The silent, flashing dialogues of the abyss outnumber all the vocalizations of terrestrial animals combined, a hidden symphony of light playing out in the dark. The study of these glowing extremophiles has reverberated far beyond the realm of marine biology, sparking revolutions in human medicine and technology. The specific chemical reactions isolated from luminous jellyfish and deep-sea crustaceans have been repurposed as fluorescent tags in genetic research. By attaching a modified luciferase gene to a specific protein, scientists can literally watch cellular processes unfold under a microscope, tracking the progression of diseases and the efficacy of new drugs in real time. The deep ocean remains a formidable frontier, a realm of crushing pressure and eternal night that continues to guard its secrets fiercely, yet the creatures that dwell within it have refused to be conquered by the dark. Through the astonishing mastery of bioluminescence, they have forged light from chemistry and built thriving ecosystems in the void. Their glowing legacy is a profound reminder of life's relentless ingenuity, illuminating the darkest reaches of our world with the unyielding will to survive.